So let me remind you what we were trying to prove. So we want to prove the Bombieri-Vinogradov theorem that if I sum over all moduli q up to q, of the difference in primes and arithmetic progressions, then I want to prove that this is bounded by x over log x to the a, provided q is smaller than some x over log x to the b, well, square root of x. Now, what we did last time was to replace this max over all the progressions mod q by character sums. So we reduced this to understanding the sum over q up to q, and then some sum over chi mod q. And so first we replace all of this by psi x chi, which is the sum of the von Mangold function weighted with this character chi n. And then this would be divided by a phi q. And then we made this argument to restrict our sums just to primitive characters. So this is over primitive characters. Then we replace the phi of q by basically something of size 1 over q. Okay? And then the goal was to prove that this is bounded by x over log x to the a. For an arbitrary a. Okay? So we reduced it to this. And our tool to do this is going to be the large sieve. So let me recall for you the large sieve from the last time, which said something like this: sum over q up to q, sum over primitive characters mod q, so this is a large sieve for in the multiplicative form. There are q squared characters being summed. In fact, we proved a stronger inequality with a factor q over phi q here, but I'm not going to worry about that. So our goal is to prove some estimate like this, starting with the large sieve in this form. So let's make maybe a few more simplifications. It's sometimes convenient to decompose various sums that you have in such a way that all the terms have roughly the same size. Okay? So it's not necessary, of course, to do that, but it simplifies some arguments and may be easier to see what's going on. So this sum over q going up to capital Q, let's decompose the sum into terms from q over 2 to q, q over 4 to q over 2, etc., etc. A dyadic decomposition. So decompose into dyadic blocks where q goes between some number capital R and twice capital R. And then R is going to be, you could take it to be 1, 2, 4, 8, etc. Powers of 2 going up to capital Q. So if I do that, there are only about log of Q values of R that I have to consider, right? And therefore, now what I have to understand is something like the max over R less than Q. And now let me put everything in dyadic blocks. Q is going to be between R and 2R. And so the 1 over Q I can replace by a 1 over capital R. And then I have to understand the sum over chi mod Q chi, and I want this to be bounded by x over log x to the a. Right? This is the problem that we have to understand. Okay. Now, okay, how do we do this, right? So we have to make use of the large sieve, but the large sieve, as you can see in the way I've written down, is like an L2 inequality, whereas what we are after here is like an L1 inequality, right? So it would be better for us if this psi x chi were a product of two things, in which case by Cauchy-Schwarz, I can then try to replace it by an L2 inequality, right? So our goal is to rewrite psi x chi as some kind of decomposition, replace this by something like a sum over a of size a. So let me write a sum over a, maybe going up to size some capital A, maybe some coefficients, let's say alpha of a chi a, and then some other coefficients b going up to b, and then some beta of b times chi of b. Right? So notice that I didn't put equality sign here. I put some kind of squiggly arrow saying that, I don't know quite what this is at the moment. Right? And, well, let's think of what the ranges for A and B might be. I'm only interested in numbers going up to x, so it's reasonable to assume that the product of A times B is comparable to x at most, right? So maybe capital A times capital B goes up to, let's say, 2x at the most, right? Let's assume this throughout. Okay? I'm not going to be interested in any other situations. This is harmless, well, I mean, assuming whatever this means. And in this generality, you can see that there is a very useless way in which I can do this. I could take capital A to be 1, and then I could take B to be x, and beta to be lambda of B, right? And then this is, of course, exactly equal to that. So at least I haven't lost anything at the moment. Okay? But suppose I now think of a sum of this type. I could now use Cauchy's inequality and try to get a bound using the large sieve. Right? So let's take that as our starting point and then think about what this, how to justify this step. Or how do I construct some kind of decomposition of this form. Okay? So suppose I do this. Then what I have to understand is a sum over 1 over r, q of size r, primitive, and then I have here right? So that might be something that I'd like to bound. Okay? So of course I haven't told you very much about, what this means, what the alphas and the betas are. Let's make some kind of small assumptions here that alpha of A and beta of B are typically small in the sense that they are bounded by some kind of divisor function. By, let's say, dk of A or dk of B for some suitable k. Right? So in particular, they're bounded by A to the epsilon or B to the epsilon. And also, you can understand something about the alpha and A and beta of B on average. Like maybe the sum of the squares will be bounded by some power of log, a fixed power of log. Okay? And then if I save enough powers of log, it'll be okay for my final application. All right? Now, let's use Cauchy's inequality. And employ the large sieve. So I have the sum over all the characters characters chi, who's of conductor about size r, and then I do replace this by this quantity squared, square rooted, and then this quantity squared, square rooted, right? So what do I get? So everywhere there's a 1 over r, and then there are two terms. And then the same thing with the B. Right? And let's use the large sieve. So if I use the large sieve, I get 1 over r here. And then from here, the n is replaced by a. So it's something like a plus r squared. That's the number of characters times the sum of alpha of a squared, right? A going up to a. And then here I would get b plus r squared times the sum over b going up to b, beta of b squared. Right? And if I make some assumption like the alphas and the betas behave like some kind of divisor function, then if I sum over a up to a or b up to b, I should be able to pick up something roughly of size capital A or capital B, and then losing some powers of log. Okay? So let's write this as 1 over, so let's lose some powers of log x to some power, what should I call this maybe? Let's call it maybe k, right? Some fixed powers of log. Maybe think of k as 100. That'll be enough. Okay? And then capital A will be arbitrary, so it could gain back whatever 100 logs that I lose in this step. Okay? And then here I would get a squared plus r squared, a. And then when I square root, I get the square root of a squared is a, and then the square root of r squared a will be r times a to the 1/2. Okay? The square root of a squared plus b squared is less than a plus b, essentially. And then the same thing here, I would get b squared square rooted, which is b, and then r times the square root of b. So far, so good. Now let me multiply these terms out and divide by the r. So I have some power of log x to the 100 maybe. And then I have 4 terms. Well, the r squared square root of ab divided by an r gives me an r times square root of ab. Then I get r times a square root of b plus r times b square root of a divided by r. So that let me write as a square root of b plus b square root of a, right? And then the last term will be plus ab divided by r. So far, so good. Okay. Now let's make use of the fact that AB is no more than x, 2x, let's say. There was no loss in assumption, assuming that. So then my bound is log x to some power k, and then I get an r root x, and then the a root b, let me write it as ab divided by square root of b. Okay, so that would be an x divided by square root of b. And then the b root a I can write as ba divided by square root of a, so x divided by square root of a. Nice and symmetric, of course, in a and b. And then the last term ab divided by r is just x divided by r. Right? And so now unfortunately I've used the letter A for 2 different things. So let me make this a C, if you like, right? Okay. This A is just an arbitrary thing. This is whatever A appears in my decomposition. Okay. If I want to make this be smaller than, so I want this to be smaller than x over log x to some power c, right? For any power c that I want. Okay? And you can now see that that my goal is that this is okay. In the following situations, provided, well, firstly, for this term to be small, I can insist that r is bounded by root x divided by some suitable power of log x. Right? If I assume that r is so small with a sufficiently large power b, then this quantity is in complete control. I have an analogous problem with this. Let's say D, right? Okay. Okay. So then this term will be under control. Then from these two terms, I must have that if A and B are suitably large, larger than some big powers of log, then those two terms would be okay. I'd be able to save enough from x over root A and x over root B, right? So I can assume, if I can assume that A and B are bigger than, let's say, log x to some power D, right? Then the second two terms would be okay. And then the last term, the x over r, would be okay, provided r is bigger than log x to some power d. Right? Okay, so is this fine with everyone? Right? So this condition is automatic because in Bombieri-Vinogradov, we are assuming that r goes up to q, and q is less than root x divided by some suitably large power of log x. Right? This condition means that most of the values we should be able to handle if we can make some appropriate decomposition of this type, right? Most of the terms you should be able to handle, except for very small moduli, right? You only have to deal with moduli that going up to a power of log, okay? There we're going to switch arguments and just use the Siegel-Wolfish theorem directly. Okay, so that'll be, we'll put everything together sometime later. So here I will use Siegel-Wolfish for smaller r. Right? So this condition is kind of the main condition that we have to worry about, right? And what's underlying this is that I need to be able to cook up some kind of decomposition of this type where neither of the terms that are involved here, both sums are of some size, right? Neither one is very small and the other one is very big. Yeah? Remember, as I said, to start with, you could have just clearly written down this as a trivial identity with A equals 1 and B equals x, right? There was no problem in doing that. And then this argument doesn't work because, you know, you don't gain from this term, you don't gain anything at all. You just get the trivial bound when you use Cauchy's inequality on the large sieve. So far, so good? Okay, but at least it gives us some plan of what to do. I want to now get some kind of combinatorial decomposition of the function of the counting function for primes, the von Mangold function, and instead of having it as just 1 lambda n, I want to rewrite the lambda n as alpha a times beta b, where n is a times b. Okay, and think of a and b both being suitably large. Right? If I can do that, then everything else would be okay. Okay, so the goal is to replace lambda n. Again, I'll write a squiggly arrow because I don't want to say what this means. To write it as something of this type. And then A and B going up to capital A and capital B, with both being large. it's not a priori clear that you can do this because, after all, a prime number doesn't have very many factorizations, right? So, and usually in a factorization of a prime number, one of the variables will be small and the other variable will be big. Okay, so how do we do this? Now, before I do this, let me make a comment that there's one more source of input that we haven't used in the large cell. Okay, and this is the Polio-Vinogradov inequality, which was covered in Dimitrius's lecture, maybe his third lecture. So if you have a primitive character chi, well, you could do this for any character chi, so long as it's not principal. Then you have a bound for partial sums of characters that this is bounded by square root of q log q. Right? So this means that, you know, if you have a long enough sum involving characters, you get quite a bit of cancellation. Okay, so maybe to keep this in, you know, why this might be useful. Suppose you think of n being roughly of size like x. Like for us, the variable, you know, sum over primes goes up to x, and the modulus of your character q only goes up to something like root x, right? Then this Polio-Vinogradov inequality is kind of summing x terms, let's say, and getting a bound of size x to the 1/4. So it's even better than square root cancellation in this range. Okay, so you can see that in certain long sums, we are getting more than the square root cancellation, which is what the Bombieri-Vinogradov theorem is about. So this is a useful piece of information, right? So even if I lose something on other sums, I can gain it back on the Polio-Vinogradov inequality. Okay, and then a small variant of this is that I can sum, you know, not just one, but any nice function. So for example, I can sum log n times chi n, and this is just going to be bounded by root q times, let's say, log q times log n or something like that. You can clearly get from here to there just by partial summation. Right? Again, you know, if I have a nice function that's not arithmetically varying, messing up with the character, I can just, I have even more cancellation than square root cancellation in certain ranges. Okay? Okay, so this will be one last thing to input. Okay, so now let me try to explain this decomposition. So this is in some ways the subtle point of the proof. The ideas go back to Vinogradov in trying to understand the 3' theorem. So that will be one of the talks, I guess, maybe tomorrow on the ternary-Goldbach problem. And again, the main idea is to create these bilinear forms. So to replace a sum over one variable by sums over two variables. Emmanuel will discuss more of that in his lectures about how you can use bilinear forms. And then over a period of time, the argument kept getting simplified until it finally got replaced by a very easy to write down identity, but then the identity is so easy to write down that you do not see what's going on just by staring at the identity, right, by the two lines. So let me explain the identity slowly. So we are interested in this quantity lambda of n, which is the Dirichlet series coefficients of zeta primed over zeta of s. So everything I'm going to do just formally, so just s is bigger than 1, say, or the real part of s is bigger than 1. Okay? Now, there are certain objects that we are going to think of as being easy in this case. And they would be things like zeta of s or zeta primed of s and when I think of these as being easy, I mean that the coefficients that come attached to these, like this 1 or the negative log n, those are things that I can understand when I think of partial sums of these, either with exponential sums, with additive characters, or with multiplicative characters, like here, right? Where you can use something like Polio-Vinogradov, or the analog of this is that if you want to sum n up to n e of n alpha, then this is just a geometric progression, and again you can just write down explicitly what that partial sum is. Okay? If I want to think of ternary Goldbach, I might want to think of things like this. Now, the flip side of it is that this guy is not so easy to understand, and in a related way, the sum of mu n over n to the s is also not easy to understand. Right? If I have a sum of mu n times chi n, I don't know how to get bounds on that in any easy way. Okay? So now, another way to think of this set of ideas is that, for a long time in multiplicative number theory, people wanted to understand objects like 1 over zeta of s, to understand where the zeta function has zeros, or to provide some zero-free region for the zeta function, right? Or failing to provide a very good zero-free region for it, the idea was to say that if you take some truncation of this series, you might want to say that usually it behaves like 1 over zeta of s, and use it to show that there can't be too many zeros very far from the critical line. Okay? So however you approach it, in many ways it became a natural thing to introduce a sum where you go up to some point m, and you take the partial sum mu n over n to the s. Okay? So it's like a truncation to the inverse of the zeta function. And then you can start with, let's see, if you take this, then you can write zeta of s times m of s. This will be equal to some sum n goes from 1 to infinity. Let's call it an over n to the s. It doesn't matter what this an is. An will depend upon m, and these coefficients an basically what you get when you multiply these two things out. Right? So this will be, let's say, this will be 1 if n is 1. It will be 0 if n is between 1 and m. And then it will be something if n is bigger than m. Something bounded by a divisor function, just counting the number of divisors of n. Right? But the point is it's 1 at 1, then 0 for a while, and then it's something else afterwards. So if I now look at 1 minus zeta of s times m of s, this is a sum of terms which are always going to be bigger than m of something divided by n to the s. Right? And the something is bounded by a divisor function. Okay? So this is with an eye towards getting some kind of decomposition where one variable is guaranteed to be large. Okay, so the sum, all the small values have been killed in this expression. Okay, what next? So let me write this quantity zeta prime times zeta of s over zeta of s I can write it as minus zeta primed over zeta of s times 1 minus zeta m plus zeta m right? Doing nothing fancy here. And then I could say, well, the coefficients that come out of this guy, they're all going to be big. Okay? And then what about the coefficients that arise out of this? Well, when I write that product down, I actually get minus zeta primed of s times m of s. Right? Just multiplying this and that. Okay? Now here what I want to make use of is that these coefficients are all small, right? And then I have a coefficient here, zeta primed of s. This is one of the easy guys that if I want to understand characters weighted with weight log n, that's very easy to understand. I can just use Polio-Vinogradov, and I'll get a lot of cancellation out of this. Okay? So this I expect in various cases to be easy. Let's say it's hope that it's easy. Okay. Now, I might worry a little bit about this. So I've achieved a decomposition here where these primes are multiplied by something, but I'm only assuming that that this guy is supported on large numbers. Maybe I'd also want this guy to be supported on large numbers. Okay. Maybe it's not strictly necessary at the moment, but let me just do it. So I wonder what I should erase. Should I erase the schedule or no? Yes? People remember? Yeah. Okay. I think I might have to erase that too. Okay, I'll erase this. Sorry. Yeah. I need not have erased this. All right. So all right. So let me go back to that. Let me write this final decomposition as what I have there. So minus zeta primed over zeta of s times 1 minus zeta m of s, and then minus one more term, minus zeta primed of s times m of s. Okay? And then here, let me just replace one of these terms by let me sum a truncation of the primes up to some point p, let's say. And then add it back. Okay. And then if I combine these two terms, then I get a sum over n bigger than p, lambda n over n to the s, times something bigger than m. Let's say I call it again n, bigger than m, of whatever this something was divided by n to the s, right? 1 minus a of n, whatever I call that. So that's these two guys, okay? Then plus this term minus that term minus this final term. Okay, if I did the multiplication right. This good? So here, m and p are going to be any parameters to be chosen carefully. Actually, not even very carefully. Quite carelessly is fine. Okay, so let me explain what the advantage of these various terms are, right? So capital M and capital P, you should think of as being small powers of x. Let's say they're both like x to the 1 over 100. Okay, there's considerable range in choosing them. So what does that mean? Then these numbers that are being counted here, they're very small numbers, counted with some weight on the primes, which I don't understand what they are, but there are very few terms in here, so this sum will be completely easy to bound. Okay, this sum, well, the capital M will be concentrated on a small set of numbers going up to x to the 1 over 100. P will go up to x to the 1 over 100. If I'm trying to get numbers up to x, then most of the numbers will have to come from the zeta, right? But those coefficients are something that I understand very well. They're just 1, right? So I can use Polio-Vinogradov to understand that. Okay. Same thing on this side. Capital M will only go up to a small range of numbers, and then the most I'll have to understand will be a long sum with a weight of log n. But that, again, is easy by Polio-Vinogradov. Okay? So these three terms are called type 1 sums. And this term is called a type 2 sum. Where we can use the large sieve, right? If I try to understand numbers multiplying out to x from terms of this type, okay, both these terms are over large numbers. So in that decomposition, when I write it down in terms of dyadic intervals in terms of a and b, neither a nor b can be very small. Both have to be, a will have to be larger than p, b will have to be larger than m. Yeah? Is this good? So this is the decomposition that I want. So if you compare coefficients, then you get an identity for lambda of n as sum of 4 terms, 3 type 1 sums plus 1 type 2 term. Okay, and it really doesn't matter what these, what the sums that arise are. They're all going to be bounded by a suitable divisor function or by logs, right? And you can write them down explicitly if you like, but there's no reason to do so. Is this good? Okay, so now let me carry out the argument. Let's keep this in mind. So what I want to understand is 1 over r, the sum over chi mod q, q of size r, of psi x chi, right? And then this guy I'm replacing by the 3 type 1 sums plus the 1 type 2 sum. Okay? So far, so good? So let's start with one of the type 1 sums. Maybe let's start with this easy one, okay? Where the primes going up to x have been replaced by primes going up to p, right? So let's say one of the type 1 sums. That would be 1 over r and then this sum over n up to p, lambda n chi n, right? But you can see this is a major victory because p is only like x to the 1 over 100, let's say, right? So I can take any trivial bound that I want for this. So trivially, this will be bounded by p. And then the number of characters that I have here is r, right? R only goes up to square root of x. So this is negligible so long as p is less than a square root of x, let's say, right? So this is completely okay if p is less than x to the half minus delta, right? And you should think p is x to the 1/10. And let's just say m is also x to the 1/10. There are r squared actually characters, right? So q goes up to size r, but for each q, I'm counting r characters. Each q, I'm counting q characters, roughly, which is r. So far, so good? Let's take one more type 1 sum. Let's consider maybe this guy there, right? The second sum. So I would have a 1 over r, a sum over chi mod q, q of size r between r and 2r. And so you would get, from the sum over zeta, you would get the sum over n going up to some interval, right? Chi n. From the m, you would get the coefficients of m, mu m times chi n, and then the same with the sum over n, lambda n, right? So what do I get? From the sum over p, I'm going to put a trivial bound, namely bound everything by p. From the sum over m, I'm going to put a trivial bound of bounding everything by m. The sum over 1 going up to some range x divided by whatever the variable for m and the variable for p was, right? I'm going to put in now the Polio-Vinogradov bound, okay, which is where I'm gaining my most cancellation. I get an r to the half times log r. Okay, so this is r to the half, another r squared divided by r, which is another r. So r to the 3/2 log r times pm. And again, keep in mind that r goes up to x to the 1/2. So this is like x to the 3/4 at most. This is a small power of x. X to the 1/10 is enough. X to the 1/10 is enough, right? So the whole thing is going to be bounded by something like x to the 3/4 plus 2/10 plus epsilon, which is negligible. Yeah, I'm doing this type 1 sum now, right? The term coming from zeta times m times this truncation over primes, okay? So when I expand it out, what do I get? I get a sum over, from the m, I would get m goes up to m, right? Something, okay? Then a sum over something times chi m. Then let's say a sum over, let's call it p now. P goes up to, not p, r. R goes up to p lambda r chi r something, right? Okay. And then finally from the zeta, I would get a sum over n goes up to x divided by m times r, right? The product of the three things goes up to x of chi n. Is that okay? So that's the type 1 sum that I have here. For this, I use the Polio-Vinogradov bound, which is r to the half log r, right? These guys, I put absolute values everywhere. Replace this by p, replace this by m. That's good. Why do I need more powers of log floating around?
Lambda m gives you enough.
No, lambda m is over a primes. The sum of lambda m is just p. It's completely irrelevant, but I think I'm right. Yeah? But they're not a's. It's just m, which is the Möbius function, mu m, which is bounded by 1. Yeah? But it's a good reality check, right? So I think as I stated, it is correct. Now, let me do the third type 1 sum. 3. It's the same deal, right? So m will go up to m, like in here. And then I would get a sum of log n times chi n going up to x over m, where I can use the Polio-Vinogradov bound. Okay? So here I would get 1 over r, sum over characters of size capital R. If I take the trivial bound, if I use Polio-Vinogradov for the zeta prime sum, I would get r to the half times log, let me put it as log of x squared, right? There was a log q times log n, so log of x squared at most. And then the trivial bound on the m sum would give me m. So this is bounded by, again, r to the 3/2 plus epsilon m. So this is x to the 3/4, this is x to the 1/10, this is fine. So this is bounded by x to the 0.9. So you see that these parameters were chosen completely without care, that anything basically will work. Okay? And then the last thing that I have to deal with is the type 2 sum. Now, I'm going to cheat a tiny bit here, but then I'll come back and we'll fix up the cheat next time. Okay? So what is the type 2 sum? The type 2 sum I can think of formally as, well, what happens when I multiply two terms, one bigger than p, one bigger than n? I multiply them out and then write down the coefficient. So I have to understand something like a sum over AB equals n, alpha A, beta B. This is the framework that we were on, right, that we looked at before. And I can assume that A is bigger than, let's say, P, and B is bigger than M, right? Okay? And N goes up to X. Right? It's not a million miles away from what I want, from what I really like, but there's this still this this kind of way in which these two variables are yoked together. Say, for example, if A is of size capital A, then B will have to go up to X divided by little a. Right? They are tied together. They're not running over different ranges. They're slightly tied together. Let me forget that for the moment. Okay? So let me now think of this. Let's think of this as a sum over A approximately of some size capital A, and the sum over B approximately of size capital B. Oh, this should be 2A of some beta B. And roughly speaking, capital A times capital B goes no more than X in size. Okay? And as I've just warned you, this is strictly speaking not accurate because capital A times capital B needs to be smaller than little x. It's really the little a times little b has to be smaller than capital X. Right? So I'll explain this tomorrow. But assuming that you're happy with this, right? The main point is these ABs go up to X, but I can also assume that A is bigger than P, which is X to the 1/10, right? And B is bigger than M, which is X to the 1/10. Right? And that's the condition 2 that I have there, that A and B should be suitably large in order to get cancellation from the bilinear sums. Okay? Okay, so let me just summarize and then I'll stop. So what we've seen is that if I use this decomposition and just use the large sieve, right, then except for this small technical point of separating variables, okay, so this is this is not very hard. There's just a small separation of variables. Then if I do that, I have a decomposition into type 1 and type 2 terms. The type 1 sums are easy. I can just bound them trivially. The type 2 sums I use the large sieve, and they're going to give me something which is good, so long as this is the last thing that will be left over, so long as R is bigger than a suitably large power of log. Right? And then in that whole range, I would have proved the bound that I want in the Bombieri-Vinogradov theorem. Okay? So we'll be almost done, except for these 2 points. One is to make this precise, which I'll sketch, and then the other one is in the complementary range. When R is small, smaller than a suitable power of log, we should just use Siegel-Wallfisch to see what it gives us in the Bombieri-Vinogradov theorem. Okay, so I'll stop here. We'll finish off the proof tomorrow, and you can come back with questions on any part of this argument before we start tomorrow as well. Okay.
Then I suggest then we wait for 5 minutes and then we start in 5 minutes with the first of the